In class activity 19A, suppose we're studying the spread of an infectious disease through a population of squirrels. The speed at which the disease spreads depends on how many squirrels are exposed to the disease, which in turn depends on the size of the squirrel population. Let C of P be the contact rate, which measures the number of squirrels per day that are exposed to the disease. Additionally, let us assume that the squirrel population in this region is given by P of T, where T is measured in weeks. The graphs of C of P and P of T are shown below. 1. Describe the general properties of the graph of a composite function C of P of T. Well, we could say that P of 0 is 300. The graph should have a vertical intercept greater than 0. And as T increases, P of T increases, so C of P of T should also increase. But C of P of T should level off like the graph of C of P does. Let's go to the next page here. Objectives for the activity. You will understand how a change in input of a composite function is related to a change in output, how the domain of the composite function g of f of x is related to the domains of the functions g and f, how asymptotes of the composite function g of f of x are related to asymptotes of the functions g and f, and you will be able to compose two functions when one or both of the functions is a rational function. The model for the contact rate, whose graph is shown, has the formula C of P equals 6P over P plus 1000. Part A, the size of the squirrel population described is given by the formula P of T equals 300 plus 20T. Find a formula for C of P of T, or the contact rate, as a function of time. Assume that T is non-negative. Simplify your answer. So P of T, let's start by using the pen. P of T is 300 plus 20T. And then the C of P function, instead of copying that all over again, I'll just highlight it there. And let's write C of P of T. So in the numerator, we have a 6 plus a P, but we know P is 300 plus 20T. And then we have a P in the denominator, which is 300 plus 20T, and then we have plus 1000. If we continue just by multiplying this out, we'll get 120T plus 1800 over, let's see, 20T plus 1300. And continuing, we'll end up with 6T plus 90 over T plus 65. Part B, as T increases from 0 to 10, describe how C of P of T changes. As T continues to increase, how does C of P of T change? What happens when T is very large? Does this agree with your answer to question 1? Well, when T is, let's start here, T is 0, C of P of 0 is 90 over 65, which is, that's about 1.4. Then let's look at when T is 10, we get C of P of 10. It ends up being, let's see, if it's 10, that's going to be 150 for the numerator and 75 denominator, which is just 2. Okay. From this information and from the graph, we see that as T increases from 0 to 10, C of P of T increases very slowly. As T continues to increase, C of P of T continues to increase. As T gets large, C of P of T approaches the line y equals 6. And this is a horizontal asymptote, and yes, this agrees with the answer to question 1. 3, let f of x be defined to be 1 over x, and g of x defined to be x plus 4, that quantity squared. Part A, for each function, find the domain and identify any asymptotes. Write the information in the table. Well, the table, let me scroll up here. The table is right here. And so we want to find the domain of f, and that's going to be all real numbers except we can't have 0. So let's put all reals except when x is equal to 0. So except 0. For g, there's no restrictions on that. So all reals is the domain. And our vertical asymptote, we're going to have one at x equals 0 for f. And there's going to be no here. So let's put none for g. Horizontal asymptote is going to be y is equal to 0. And again, none for the g function. Part B, use the information from part A to determine the domain of g of f of x. Add a column to the table to display your answer. So over here, this last column is going to be g of f of x. So the domain of g of f is the same as the domain of f. And if you think about this, since 0 is not the domain of f, it can't be an input into the function. Therefore, could not be an input into g of f of x. Since the domain of g is unrestricted, there's no additional restrictions on inputs from the function g. So we can state that this is going to be all reals except 0 again. There we go. For vertical asymptotes, let's see, part C. Since f is undefined when x is equal to 0, g of f is undefined at x equals 0. Given that f has a vertical asymptote at x equals 0, it makes sense that g of f will also have a vertical asymptote at x equals 0. Part D, as x increases without bound, the function values go, the function values of f go to 0, okay? But if f goes to 0, then the values g of f will go to not 0, it's going to go to y equals 16 as x increases without bound. Similarly, if x decreases without bound, the function values for g of f will go to y equals 16. So it follows that g of f of x has a horizontal asymptote when y is equal to 16. There's one more part here, and that is part E. It says use composition to find an expression for g of f of x using a graphing calculator, graph the function g of f of x, and use the graph to verify your answers. Okay, so if we have g of f of x, that's g of 1 over x, which is 1 over x plus 4, and that quantity is going to be squared. So I have this graphed in, oops, our calculator under the y equals screen, and you saw the graph already, and that's what the graph looks like. And as far as there seems to be a vertical asymptote, which we knew, at x equals 0, and also a horizontal asymptote at y equals 16. And that looks like that agrees with what we see in this picture here. So let's go back here, and that is the end of this video.